everyone. Welcome to our first mathematics video for Math 2710W. I'm going to talk about some of the highlights from Chapter 1, Section 1 of Hammock's book. I'm counting on everybody reading the textbook, and you've all said that you were planning to do that. So if anything I say doesn't make sense or you'd like more explanation, you can put a question up on Piazza or email me. Although I'll probably refer you to Piazza, and I will be happy to talk at greater length at any of the points which come up. And of course that applies not just to this, but to any future video discussion that we might have. So, Chapter 1, Section 1 is about set theory. The first chapter of this book is about set theory. Set theory is the foundation of mathematics these days. And although there is a pretty subtle and complicated theory of sets, we are not going to get into that. We're going to work with what we might call a naive idea about sets. And in this form of naive set theory, a set is just a collection of things. And the collection of things, the things in the set are called its elements. And I'm not going to even attempt to define what I mean by a collection, and I'm not going to attempt to define what I mean by things, although you'll see many examples, and you can see that this is an extremely general idea. So a set is completely defined by its elements. So two sets are the same exactly if they have exactly the same elements. Knowing the elements means knowing the set. So as an example, we could define our set to be the collection of books in Babbage Library. Now, that certainly seems like it's a good collection, but you could raise a few objections. For example, you could say, well, what do you mean by in Babbage Library? Do you mean in the collection, in the catalog, physically in? Are we only talking about the books that the library owns? What about books that random people might have brought into the library, which are their own personal possessions? So a very important point about sets is that it's fine to say that they are a collection of things, but they have to be a precisely defined collection of things. So we could clean this up. We could say that it's the collection of books physically present in Babbage Library But even that's not completely specific because, of course, that changes. People bring books in and out. So let's make it as precise as we possibly can by saying right now. And now we have a well-defined collection of books. And if I ask you, is this book an element of the set? I can ask you, and by now I mean at 4:37 p.m. when I'm recording this video, which is July 28th, 2020. So in order to decide if a book belongs to the set, we would need to know if it was physically present in Babbage Library at 4:37 p.m. on July 28th, 2020. But at least that is a specific question which we can answer. So there are a couple ways to describe a set. One way is to actually just list out its elements. So for example, we can describe a set A by saying it's the set whose elements are the numbers 1, 2, and 3. And we've written that here. So there's some special notation associated with sets. These curly braces mean the thing that is between them is a set. So 1, 2, and 3 are between the curly braces, so they make up a set. And we've named that set A using equals. And you see the curly braces, one property of them is because a set only depends on its elements. Two sets are the same if they have the same elements. The set 1, 2, 3 and the set 3, 1, 2 are the same because they have the same elements. So there's an automatic understanding that if you list a group of elements that make up a set, the order doesn't matter. All that matters is what things have you listed that make up the elements of the set. One other really important piece of notation in this business is the symbol, this symbol, which you read is an element of. So it looks a little bit like a backwards 3 and a little bit like a Greek epsilon, although strictly speaking it isn't either of those things. If you're writing it by hand, it's sometimes hard to tell it apart, but you can make a kind of a C with a line in the middle. That's good enough. And in English, you literally read it as is an element of. So if you write 1 in A, this means 1 is an element of A. You can put a slash through it like you do with equals, and then it means it's not an element of. So 5 is not an element of A. You can write like this. Remember that A was the set from the previous slide, consisting of 1, 2, and 3. Now, if the only thing, let's get a few examples of sets that we'll be able to rely on for the rest of the course under our belts here. So the first basic example, and this is, again, standard notation, the natural numbers is the set of counting numbers that starts with 1, 1, 2, 3, and then I've written dot, dot, dot. Dot, dot, dot isn't very mathematical, but in this case, I hope that it at least tells you what it is that I am trying to say. I mean the full set of counting numbers 1, 2, 3, 4, 5, 6, 7, and so on. If you're trying to write this fancy n by hand, one way to do it is like this. You make the crossbar doubled, or you can just write n, capital N. But you will often in math texts see this fancy font for the natural numbers n. In addition, you have the integers, which are the positive and negative whole numbers together with 0, and I've written those here. Those always get the letter Z for their description. That goes back to the German word Zahlen, which means number, and somehow that initial Z got attached to the set of integers. And then we have the set of rational numbers, which are the positive and negative fractions in 0. So I didn't try to list Q because it's not really clear what order there might be, but for example, 1/2 is in Q, -3/5 is in Q, but also all the integers, all the integers are in Q as well, because they are fractions. 100, which is the same as 100 over 1, is in Q, and -37 is also in Q. So if you want, you can think of each of these sets as getting bigger. The natural numbers, the integers, and the rational numbers get bigger and bigger. We know quite a bit about these sets. We know, for example, that you can add and subtract and multiply and divide at least some of the time. And for the rest of the course, we're going to take the basic rules of addition and multiplication for granted. So we're going to take for granted the fact that A plus B equals B plus A. That's the commutative law. A plus the associative law, which says that you can group terms and get the same answer. This is the associative law, and so on. I'm not going to go through these. I hope that you have seen them in your past. If you have not, if these words, commutative and associative, don't mean anything to you, then I think you should either ask or look it up. And I will probably ask a question about them just to make sure that people are comfortable with that terminology. Now, the only way you had to list elements of a set was by enumerating them, you would be very tired very quick. And also you'd have to deal with that dot, 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 which might not mean the same thing to everybody who looks at it. So a more precise way to define sets is what the book calls set builder notation. But a fancy word for it is predicates. So I'll explain what I mean. So in order to use set builder notation, you have to have a set to start with. And we've got a few, like the integers and the rational numbers. And set builder notation says you can select elements from a set according to some rule. And you would write it, for example, like this. So the way you would read a sentence like this is, take all the elements x that belong to the given set. So take all integers z, take all integers x in Z. And then there's a condition which is separated by a colon or sometimes by a vertical bar. But require, and the condition means only keep those that pass the test. And in this case, the test is that x is bigger than or equal to 0. So the way to read this is that this set is the set of integers which are bigger than or equal to 0. So, for example, 13, let's call this set A. 13 is an element of A, but negative 7 is not an element of A, because negative 7 doesn't pass the test, x is bigger than or equal to 0. So one mental picture you can have in mind is that you're going down the list of integers and picking out those which pass the test. Sometimes these predicates can be complicated, and you may not even be able to figure out whether the set is empty or not. I mean, a famous example of that is, I think it goes back to a question like, I mean, a perfect number, this is just a little side example. A perfect number is a number, an integer, n, which is equal to the sum of its proper divisors. So for example, 6, the proper divisors of 6 are 1, 2, and 3, and 6 is equal to 1 plus 2 plus 3, so 6 is a perfect number. 28, the proper divisors of 28 are 1, 2, 4, 7, and 14. And if you add these up, you get 21, 25, 27, and 1 is 28. So 28 is a perfect number. And you could make a set, X, which is the set of all n in Z, such that n is bigger than or equal to 1, n is odd, and n is a perfect number. Now, that looks perfectly reasonable. I mean, I'm saying go through the integers and look for examples which are perfect numbers and are odd. The only problem with this set is that nobody knows whether there is anything like that meets those conditions or not. So we don't know an example of an element of the set X. But not only that, we don't even know if X has any elements of it at all. It's an unsolved problem in mathematics. So you can get yourself into trouble pretty quickly with these predicates. They can be deceptive. But nevertheless, this set is well defined, even if we human beings don't know whether there are any elements in there or not. Just to give you a few more examples which don't involve numbers, which are perfectly reasonable examples of sets, the alphabet is a great set. So the alphabet, this is the set of at least the Roman alphabet, or the English alphabet, consists of A, B, C, down to X, Y, Z. Now, I should, we could worry about whether I mean capital or lowercase letters, but I think the alphabet is A through Z. Whether it's an uppercase or lowercase, that's more a matter of typography. Or you could have the set of words in English. So this is a very large set. It has things like the and if and frigate and whale and so on in it. Or you could have a set of people, the set of people now living. Now, I guess, could mean now when you're watching this video or now when I'm making it, which is in July 28th, as we know. But that's a perfectly respectable set, because if I give you a person and they're living, then they're an element of the set. And if they're not living, then they're not. I could define the set of chairs in my house, and as long as we're absolutely clear about what is a chair, and there's no ambiguity, like I have some little, like, I guess you'd call them maybe stools that have no back. I mean, if you count that as a chair, then that you'd have to include that in the set or not. And remember that one characteristic of a set is you can determine exactly what its elements are. So if you know exactly what you mean by a chair, then the set of chairs in my house form a set. There's one super important set which everybody needs to know about, and it's the set that has no elements. And this is, I mean, to the extent that there's an axiom in set theory, there are axioms. I mean, this is, you can take this as a given to you, which is that there's exactly one set which has no elements, and that we call it the empty set. And it has a special symbol. You can either write it like that, or you can write it as a set with no elements at all. There's a couple important things to think about here. One is that there is an empty set. In other words, it's legitimate to have a set with no elements. That maybe wasn't clear before, but for a lot of reasons, it's really important to have that in the theory. So we're going to allow there to be a set with no elements. And the other thing is there's only one set with no elements. Meaning, remember, a set is determined by its elements. So if two sets have the same elements, they're the same set. Well, that's a little bit weird, maybe, if the set has no elements at all. But we're going to interpret the rule that two sets which have the same elements are the same set to mean that if a set has no elements, it's the empty set. There aren't multiple empty sets out there. So any two empty sets are the same set. Basic operation you can ask about a set is how many elements does it contain? We're going to talk a lot more about this at the very end of the course. But for now, we're going to rely on the naive notion of what this means. So a set like 1, 2, 3 has 3 elements. A set like the integers is infinite. It doesn't have a finite. So you can for now, you can divide sets up into infinite sets and finite sets. And finite sets have a number of elements in them. And we use this absolute value sign to indicate the size of the set, the number of elements. So you'll sometimes see people write, if X is a set and the number of elements in X is less than infinity, this means that X is a finite set. It has some number, not specified, of elements. One set which I've not talked much about in my examples of numbers is the set of real numbers. We work with real numbers a lot in calculus. So you think about the number line here. Here's the real numbers. And they get a fancy R. So the real numbers, the integers are real numbers and the rational numbers are real numbers, but there's a lot of other real numbers. I mean, for example, pi is a real number and e is a real number and the square root of 2 is a real number and so on. Saying exactly what it means to talk about a real number is a complicated business and we will not get to it in this class. If you take analysis after this class, you'll get a formal definition of what the real numbers is. And it's very interesting how that's done. For now, we're going to just think about real numbers, for example, as being given by, a real number is given by a number which has a possibly infinite decimal expansion, like 375.121371416. And here's this infamous ... again. I'm not telling you what those digits are, so you don't really know what this number is. There are other ways of getting real numbers where you sort of know exactly what they are, but they often come from limiting calculations, like the fact that, I mean, e, if you remember from calculus, e is the limit as n goes to infinity of 1 plus 1 over n to the n. And that's great, and it means that you can approximate e to as many decimal places as you want if you have a good computer. But does that mean you actually know what e is? It's a tricky business. So again, we're going to rely on the real numbers in the same way that we did in calculus, as a kind of an intuitive object which has the property that any decimal expansion like this gives you a real number. And we're going to also take for granted that there exist numbers like pi and e, which are elements of the real numbers. One nice way of making subsets of the real numbers is using intervals. So this is all laid out on page 7 of the text, and I'm not going to go through every one of these things, but basically you use square brackets like this to mean greater than or equal to, and you use curly braces like this to mean less than without the equal to. I better not put that there. That's kind of confusing. But so the fact that there's a square bracket here means that it's x is, these are supposed to be the numbers between a and b, and then the curly braces tell you what to do at the end. So for instance here, these are the numbers between a and b. The fact that this is a square bracket means you keep b in, and the fact that this is a parentheses means that you leave a out. And then you can also use infinity. Again, this is standard notation. When you write something like a infinity, this means all the numbers between a and infinity. So everything bigger than a and as big as you want. So there's no condition on the other side. And the fact that this is a square bracket means that here you have greater than or equal to. And the fact that here you have a curvy bracket, so this would mean all the numbers, actually this is a typo. This should say minus infinity to a. So this means all the numbers from, if you think of that number line, we're sort of thinking about negative infinity out here and infinity out there. You may have seen that in calculus. So minus infinity to a means here's a, everything to the left of a out to minus infinity. And the fact that this is a curvy brace means we're going to leave out this point. We're going to leave out a itself. And the fact that here we have a square brace means that we include a. So these are all chosen from the real numbers themselves. They're all examples of that predicate notation where we start with the set of real numbers and we pick elements that pass a certain test and keep them. So I wanted to look at a couple of examples and problems from the text just to maybe give you something to hang on to in all of this. So let's look at this. This is example 1.1, and I'm calling this a claim. A claim is something that you're supposed to decide if it's true or false. So claim means I am saying it's true. Do you believe me? That's what claim means. So this is an example of set builder notation, although it's a little bit different than some of the ones we did before, because you see what it's saying the way to read this is take a number n in the integers and square it. So it's a little bit confusing because in the other ones we would have written, we would have said take elements of the integers and ask if they pass a certain test. So here we're actually writing a little bit differently, and we're saying as n runs over the set of integers, take the squares of those integers, and that's your set. So if n is 0, you get 0. If n is plus or minus 1, the square is 1. If n is plus or minus 2, you get 4, and so on. So if I was going to say this in words, I could say take the set of squares of integers n in Z. My set A is the squares of all integers and if you think about it for a minute, this n in Z, what if instead of saying n in Z you said n in the natural numbers? So is that the same? Well, remember what the natural numbers is. The natural numbers starts with 1. So if you use the same logic, then you're saying start with 1 and square it, and then take 2 and square it, and then take 3 and square it, and then take 4 and square it. And you don't get quite the same thing, because since n is restricted to the natural numbers, the first number you're going to get here is 1. and then you're going to get 4, and then you're going to get 9, and so forth. So whereas 0 is included here because 0 is the square of an integer, 0 is not here because 0 is not the square of a natural number. On the other hand, if you took n in the rational numbers, well, then it's hard to write down because, for example, 1/4 is 1/2 squared, and 4/9 is 2/3 squared, and so on. So if we let x be the set of n squared for which n is in the rational numbers, then 1/4 is in x and 4/9 is in x. What about 1/2? In other words, what is that really? If I'm asking you, is 1/2 in x? Well, what I'm asking you then is 1/2 equal to n squared for is some n in the rational numbers? Now, maybe you know the answer to that question. That's like asking, is 1 over the square root of 2 a rational number? The answer to that is no, and we'll see more about that later. But the point I'm trying to make is it's not always completely straightforward to decide whether, just because you've written this down, whether or not you can tell if a particular number is in that set. I mean, for instance, I could ask you, let me add another page. I think I know how to do that. I don't know how to do that. I'm going to learn how to do this better later, but let me make a little space up here. So we could ask, is 47126913874 in the set of n squared such that n is in Z? So to answer that question, we need to know, is this number 47126913874 equal to n squared for some n in Z? In other words, is this a perfect square? And I guess I suspect it's not, and if you use your calculator, you can probably decide if it is or it isn't. But again, I want to indicate that there's an implied, there's a lot of implied thought in a statement like the set of n squared for which n is in Z. Maybe I'll make one other comment about this, which is we could also have described this as the set of n in R such that the square root of n is in Z. Now this says that we're interested in real numbers whose square root is an integer. And if n is in R and the square root of n is in Z, that means that the square root of n is equal to some integer z, so n is equal to z squared, and z is in Z. In other words, n satisfies this condition. It's the square of an integer. And if we write it this way, it looks a little bit more like the kinds of predicates that I talked about before, where you go through the real numbers and you apply a test. But we would have to be careful to make sure that these two things really are the same, and that's how do you decide if two sets are actually the same. What you really need to do is, again, a topic for later. So for now, the goal is really just to be able to read these claims and figure out what they say. Let's look at another example. So this is example 1.2, and the problem says to describe the set of A is the set of 7A plus 3B for A, B, and Z. So this is another one of these sets where what they're telling you is that as A and B run over the integers, you're going to take 7A plus 3B. Well, so for example, how do you tell if a number's in the set? So an integer, let's look at if we take a equals 3 and b equals -1, then 7a plus 3b is 21 minus 3 is 18, right? So 18 is in A. Or we could take A equals 5 and B equals 2, and then 7A plus 3B would be 35 plus 6, which is 41. So 41 is in A. Well, this is kind of a painful process. What about a number? Maybe we could try to figure out if there's a number that isn't in A. Like let's pick a number at random. Let's pick like 14. Is 14 in A? Well, can we write 14 as 7a plus 3b? Well, actually we can, right? 14 is 2 times 7 plus 0 times 3. So if I take A equals 2 and B equals 0, then 14 is 7 times A plus 3 times B, and so 14 is in A. What about 11? Well, 11 is, can we think about what 11 might be? If you take you can't have A as 1, because if you take, let's look at some examples here. If A is 1, then this is going to be 7 plus 3b, but 11 minus 7 is 4, which can't be a multiple of 3. If A is 2, then this is 14, and 11 minus 14, that seems like it might work, right? 11 is 14 minus 3. So it's 2 times 7 plus 3 times minus 1. And so that tells us that 11 is in A. So I'm not going to, if you go to the book, you will see there that they work out that actually A, every integer is in A. So, for example, 1 is in A. 1 is 7 times 1 plus 3 times minus 2. And so in the end, the answer to this problem is that A is the integers. So I think everybody needs to go and read this, this carefully so that they can see how that argument works. Because it's not obvious when you start out that, in fact, every integer can be written in the form 7a plus 3b. So the conclusion of this is that a equals z, and that means that every integer n is equal to 7a plus 3b for some a and b in z. Let's look at one more example. This is a problem from the book. It's problem 7 from section 1.1. And they ask you to describe this at x squared plus 5x equals minus 6, where x is real. So in the back of the book, they give the answer minus 2, minus 3. How did they get this answer? Well, first of all, we should check. Minus 2 squared is 4, plus 5 times minus 2 is 4, minus 10 is minus 6, and minus 3 squared plus 5 times minus 3 is 9, minus 15 is minus 6. So in fact, that tells us that both minus 2 and minus 3 are in the set. They both pass the test. How do we know those are the only answers? Well, we can actually use a little algebra here, because we can solve the quadratic equation x squared plus 5x equals minus 6, which is x squared plus 5x plus 6 equals 0. And this actually factors as x minus 2 times x minus 3 equals 0. And so, sorry, x plus 2 times x plus 3 equals 0. And so the solutions in the real numbers are x equals minus 2 and x equals minus 3. So what about if you replace R with Q in this definition? So it's asking not for the set of x in R, but for the set of x in Q, such that x squared plus 5x equals minus 6. Well, again, we know the only real solutions are minus 2 and minus 3. So if we had a rational solution, it would also be a real solution. So both of these solutions are rational numbers, so they both belong to this set, and there can't be anything else. So, because if there were others in the rational numbers, they would be in the real numbers, and we already ruled that out. So minus 2 and minus 3 is again the answer for the set of x in the rational numbers if x squared plus 5x equals minus 6. But what about if we replace it with R with n, with the natural numbers? Well, in that case, the only real solutions are minus 2 and minus 3, and neither of those are natural numbers. So there are no solutions to this. The set of x in the natural numbers, such that x squared plus 5x equals minus 6, is the empty set. There are no solutions to that equation where x is required to be a natural number. I mean, you could think of that directly, because if x is a natural number, then x squared plus 5x is going to be positive. So it can't equal minus 6. So there's a whole bunch of other problems at the end of section 1. I think everybody should take a look at those and get back to me with questions.